Hello and welcome to another video, this time on the MAT 2007 questions F to J. Sorry, I should say that. MAT 2007. This is questions F to J. Okay, yeah, like I said before in the last video, I feel like the questions are a little bit easier with the older ones. Maybe it's because I've just done them before. I don't know. I really don't know. I will say this was the only one I got wrong. Um, Not because I didn't know what to do, but because I misread my own handwriting. You know, careless slip-ups. They happen all the time to me. I don't know how sort of careful you are, but I am terrible for them. I really am. I'll show you what I did actually. I was like, well, clearly these are all powers of two, so surely the secret here is to write it all in powers of two. And I wrote 2 like that there, and I wrote 2 to the 2x, and I wrote 2, well, this is going to be plus 4 times 2 to the x. I just read that 2 there as an X, and then ended up in all kinds of trouble. So yeah, don't do that. That's one of the things I'm really bad with in maths. I'm just terribly slapdash. You know, I sort of like rush into things, and because of that, I end up in all kinds of trouble. So, okay, provided I haven't misread my own handwriting here, what we can see straight away here is this is a disguised cubic. Yeah, disguised quadratics, disguised cubics. You want to be on your guard for them always, not just in these kinds of papers, but also in A level in general. You know, I mean, we have disguised quadratics all the time with trig. We can even have them with log functions, with exponential functions. So they shouldn't be too unusual. And sometimes it helps to let u equal, say in this example, 2 to the x, because then you can see you've got a u cubed here. You've got a 4 here. We'll leave that as 4 because actually it's not that much of a bonus turning it like that. That's going to be u squared, and this is going to be 4u. Yeah, and okay, so we've got 0 equals, oh yeah, let's do it as u cubed minus u squared minus 4u plus 4. Now, sometimes with cubics, you know, you might start stressing, thinking, oh no, I've got to factorize a cubic. But remember, we've got a factor theorem to help us for this, yeah? And especially if you spot an easy factor straight away, that should be a big signal. I've noticed as well with some of the papers, some of the step papers, for example, they're starting to hide the factors with numbers like a half or something like that. So you've got to plug in a half to find, you know, to find the factor. Now, what factor can we find here? Well, you know, you're probably best checking 1 first. 1 minus 1 minus 4 plus 4. Oh, that didn't take long. I genuinely am doing this one live just because I messed it up and I could see, oh, you know, I turned that 4 into a 2 to the x. But yeah, anyway, so let's clearly we can see, you know, u minus 1 is a factor because u equals 1 is a solution. And so let's factorize it. I don't know how you factorize these. If you're doing long division, seriously, don't do that anymore. Like, there are much quicker ways. Do short division or find some way to divide this by u minus 1. This is my way. I'm just like, that must be a u squared to give you u cubed. Yeah, that gives you a minus u squared, which we want. That's good. Then we want a minus 4u, so we need a minus 4 here. And sure enough, it gives us plus 4 at the end, which tells me I've done it right. You know, you don't want to be faffing about with long division there. Okay, so what do we have? We have u minus 1, u minus 2, and u plus 2, because we've got difference of 2 squares there. Now, you might start thinking, 3 solutions. Hold your horses steady on, because this is going to give us 2 to the x equals, 2 to the x equals 1, because we want this to be 0, or 2 to the x equals 2, or 2 to the x equals minus 2. Now, that's got a solution. That's got a solution. You know, that is x is 0. This is x is 1. Does this have a solution? I don't think so, because obviously the graph of 2 to the x is never negative. Looks like that. And so 2 real solutions, we're done. Okay, G, these ones, the graph ones, quite often I find you can rule out some like laughable answers. I mean, let's take a look at this. Pretty much going on what we were just saying before, the graph of 2 to the minus x, well, here's 2 to the x, look, I just drew it. 2 to the minus x is just a reflection in the y-axis because all the x coordinates have changed from positive to negative. So that's going to go down like that. And my point about this, drawing this 2 to the minus x, is it's strictly positive. That is greater than 0 always. What about sine squared? Well, that's greater than or equal to 0, yeah? In other words, y can never be negative, so ignore b. Yeah, ignore B. That's always positive. That's always positive. Ignore B. The other thing we should do is ask ourselves, when x is 0, what is y? And, 0 squared is 0. Sine of 0 is 0. Square 0 is 0. 0 times anything is 0. So D is definitely well out. So it's just a choice between A and C. Now, I could faff around doing product rule here, but I've got to be honest with you, I didn't. I really didn't. I just kind of figured like this. This is definitely going to have its turning points, not where 2 to the x has turning points or 2 to the minus x has turning points, because it doesn't have any turning points. Yeah. So this isn't going to like control the waviness of this function. It's going to be the sine squared, which controls the waviness, if you like. And where do you get peaks and troughs for sine x? Well, the first peak occurs when x is pi over 2. Yeah. So I kind of thought, well, I'll need to have x squared equal to pi over 2, in which case x is going to be root pi over 2. And I estimated that half of pi is like 1.5 and a bit. I'm not very good with pi. I don't know it to many decimal places, maybe 3.14, I think. And then the square root of 1.5, well, about 1.25, I guess. It's slightly more than 1, isn't it? And look at this, the reason I was doing that was because this one is less than 1 on the peak. This one is more than 1 on the peak. So I went for A there, and I'm pretty sure my reasoning's all right. I can't see what's wrong with it. If you did the product rule on it and did it the hard way, well played. But yeah, that was my reasoning there as well. I just figured you're going to get peaks and troughs in the same place as the sine curve. Okay, so H. This one's more interesting. My first thoughts here was, well, it looks like simultaneous equations, doesn't it? They've even laid it out like that. Now, so what I did first was I just subtracted the equations. So I did 1, 0, 3, f of, I took the 3 out. Who wants that hanging around inside? So 1, 0, f of x dx minus 2 and 0, f of x dx. So I've done that one minus that one. Now this one minus this one is just going to leave you a positive between 2 and 1, f of x dx, because you can think of that 2 flying outside the integral. You always want to do that trick with integrals. So you're doing 2 lots of something minus 1 lot of something. So obviously the answer is 1 lot of something. And this equals 6. That's what I did first. And then I thought, hang on a second. Because if you go from 0 to 1, and then you go from 1 to 2, that is obviously the same as integrating from 0 to 2, because that will find you the area straight away. Yeah, so that's a rule I can use here. So what I thought was I'll borrow one of these 3 and add it to this one, giving me one of those which cancels that out. That's what I thought. So I'm going to have 2, 1 and 0 f of x dx. So I've used this kind of trick here. And then this one, I borrowed one of these to add it to that to make one of these which is positive. So I'm just going to have now equals 6. And so between 1 and 0, f of x dx, well, that must be 3. Yeah. Now you might think, but that's not what I want. I want from 0 to 2. But of course now I can plug stuff in, can't I? Because I know that this is going to equal, if I can just delete what I've got up here, I now know if I think about the 3 coming out that this bit's going to be 9, and therefore that one must be minus 2. And so on its own it must be minus 1. Sorry, dx. I should write all those down. I'm dead slapdash on the short answer questions, I really am. And if this one is minus 1, when we add it to there we get 2, and so the answer must be D. Yeah, because if this one's minus 1, I'm just going to add it over there, make 2, and that equals 2. So that one's, it was an interesting one. I sort of sat here for 30 seconds. I did something silly at first. I'll show you what I did. First thing I did was I thought, I'm always excited when I can see difference of 2 squares, because it's like, so often the answer's about difference of 2 squares. So I started factorizing this as, a difference of 2 squares when I took that onto that side. But of course, you don't want to do that the best way of doing it is to just straight away think, well, hang on a second. That's immediately told me the maximum value of the left-hand side. It must be equal to 1. Definitely can't be more than 1 because you're taking away a square. They love doing these kind of things where you take away a square and you can see that it's a maximum. So, the right-hand side, the biggest value it can take is 1. Yeah, and if you're wondering what value of b generates that, you're probably thinking, are you sure that can be 0? Yeah, I'm sure, because if I set b equal to 1, log base 10 of 1, log base anything of 1 is always 0. There might be some side edge cases there where that's not true, but like, we're log base 10 of 1, and that's definitely 0. And so I can make that 0, in which case log base 10 of a all squared is going to be a quarter, in which case log base 10 of a is going to be the square root of a quarter, which is a half, in which case a is 10 to the power of a half. So I guess the answer is root 10. Okay, the last one. This is the easiest J question I've seen. So you do get the odd one actually, which is quite easy. I suppose if you notice it, though, isn't it? It's all well and good saying it's easy when you know the trick. Like when you don't know the trick, it's really, really difficult, isn't it? I was given a question today from the Tamu actually, which I'm going to work on in a second when I pop inside and greet my family for the few minutes a day that I get a chance to say hello to them. But yeah, I'm gonna work through that again. So James, if you're listening to this, I'm gonna have another go at that rectangle problem. That sounds quite interesting. Anyway, what do we notice here? Well, firstly, we've got the sum of the first 100 numbers. Now, if you haven't heard the story about how Gauss added the first 100 numbers when he was 6 or 8 or however old he was, he basically went like this. You must have heard this story before, but I already just know what the sum from 1 to 100 is because I tell my classes this story all the time. It's 5050. Yeah, so you got 1 and 100, 2 and 99. There's lots of ways of doing it. I sometimes put a 0 in here and I say 1 and 0 and 100, 1 and 99, 2 and 98. You can obviously link them up, can't you? All the way till you get to the middle where you're going to get 49 and 51. How many pairs from 0 to 49? There's 50 pairs there. Oh, and then you've got a 50 in the middle. So you've got 50 hundreds plus a 50. That's 5050. I'm sure you'll have heard that story before. There's loads of other ways of adding up the numbers from 1 to 100 though. Use the sum of an arithmetic sequence formula because it is the sum of an arithmetic sequence. Or use the fact that these are triangle numbers and use, nm minus 1 over 2 or nm plus 1 over 2. Sorry, I'm thinking about graph theory there where we often use nm minus 1 over 2. But anyway. Hopefully you can see that the sum. Oh, well, here's another way you can do it because the formula here is nm plus 1 over 2. Did I say nm minus 1 over 2? That's definitely wrong. So if that's 100, you're going to do 100 times 101 over 2, which is 50 times by 101, which is 5050. Okay, so we know that, yeah? And then we know n is greater than or equal to 1. Well, let's say n was equal to 1 because that will give us like if you like, the smallest the largest that k can be. Yeah. Let's just look at n equals 1 for a second. What are we going to have? Firstly, how many terms are in this sequence? Well, these are the square numbers, 1, 4, 9, 16. So the fourth term is 16. So the 10,000th term will be the 100th term. And you can see that anyway, because if we finish on 100 there's 100 terms in that sequence. Yeah. Now, if you had 100, yeah, here, then you're told this inequality is true. So what we now know is true is that 5050 plus well, let's set n equal to 1. And what are we going to have here? We're going to have 5050 plus 100, and that's got to be greater than k. Yeah. Well, that's 5150 is greater than k. Yeah. Now, this is why I'm certainly looking at that and thinking that that looks true. Now, we were told that n is greater than or equal to 1 though. Well, when you think about it, when n is greater than 1, it's definitely going to be larger than that because it's not just going to add up to 100, it's going to add up to a lot more than that because we're doing big powers there. So yeah, sure, the answer is just D. It's just obvious. It's k is less than 5150. And that's it. That's this video. Hope you enjoyed it and I hope it was useful. Anyway, good luck in the mat, everyone. Hope it goes really well. Remember, and I would say this, I'd like to say this at the end of all of my videos really, don't just watch videos, practice. Always do these questions first and have a really good go at them before you watch any of my solutions. Your solutions may well be different to my solutions. Brilliant. That's awesome. You've probably found some better ways of doing it. You probably make fewer mistakes than me. Brilliant. Do it, but smash the math paper. I hope it goes really, really well, regardless of where you're applying to uni as well. I don't care where you go to the uni. I just want you to beat that paper. Well done.